Hello, everybody. Welcome to the wonderful world of the INESC TEC webinars in power and energy. And in this new year, with this new webinar, I am very happy to host this session today, where we have two extraordinarily and interesting persons, researchers, colleagues, that are going to share with you some of the advances in the state of the art of very interesting topics. Allow me to share with you some details on the bios of the speakers here. So the first speaker will be Dr. Ricardo Besser, and as you can see, he was born in Portugal, and has an interesting career in terms of education, going from power system engineering to economics and data analysis, and then to a sustainable energy systems PhD. He is today one of the youngest and brightest researchers from INESC TEC, in coordinator of the Center for Power and Energy Systems at this organization. He is devoted to a lot of work in reviewing papers, and is also the editor for the IEEE transactions in sustainable energies. Of course, his research interests are around data, linked to renewable energy, energy analytics, smart grids, electricity markets. And I am very sure that you will be very pleased to hear some news, exciting news that he's going to bring to you. And later, I will be able to also introduce to you in more detail Dr. Pierre Panson. But for the time being, I will stick with the next speaker. I must warn you that there will be a break between presentations, and an opportunity to ask questions, a Q&A moment. And I would ask kindly for you to write questions during the sessions, write your questions in the Q&A section, then preferably not using the chat facility. And this will run smoothly. So we have 20 exciting minutes in front of us. So welcome again, and I am going to give the floor, the screen, to Ricardo Besser. Please, Ricardo, carry on. I'll just stop sharing my presentation.
Okay. Okay, so good afternoon to everyone. I will talk about federated learning for smart grids. I will address or cover two main use cases and topics, but I will also give a flavor of the potential of this area. Okay, some motivation and concepts. One big motivation is that we have an increasing volume of geographically distributed data. So nowadays, it's not just electrical assets like wind turbines, PV panels, smart meters, but also other types of data, even from other sectors, not just electricity, which is the case of mobility. And we also have the IoT, and even the smartphones can actually be now sensors with data that can be valuable for the electrical grid, for grid operation, but also for the energy sector. So we have all this kind of heterogeneous data that we can exploit and extract a lot of value, but there is three main barriers. One is data privacy and confidentiality. So most of this data, it's either private because it can have some personal information about citizens, but it can also be confidential. So it is owned by a company and have commercial value. And this will be the focus of my presentation. Then there is also a lack of monetary and non-monetary incentives for data sharing. This will be the focus of Pierre's presentation, and also lack of business cases for collaborative analytics. We learned a lot about collaborative analytics, but then if we have to think on what use cases and business cases we can find, it's not so simple or straightforward. So I will explain here the concept of federated learning. What you have here is a typical setup on machine learning. We have a set of data and we learn our model from this data. What federated learning is doing is moving from this centralized approach, and we break the data into subparts of the full data set. Then we learn each model locally on this data, and then the information that is learned locally is aggregated in a master model. So we are able to break data by data sources or data owners, make local learning there, and then we aggregate everything in a single model. This is something that nowadays several companies already do this, in particular for smartphones, where you have data from different consumers and you want to extract some relevant information from that data. This is called horizontal federated learning. So in horizontal federated learning, you have two different data owners, A and B. They share the same features, but you want to have different records that comes from the two data owners. So this means that this is called horizontal federated learning. So the owners, they share the same features, but they have different records, and you want to combine all of those records. What will be the focus of my presentation is not that one, is vertical federated learning. In this case, the two data owners, they have different features of data. So they have the same number of records, in this example 3, but they have different features, and what you want to combine are features that are distributed by different owners. And this is the focus. And for the case of time series, which is what we will address, it's quite challenging, in particular if you are doing forecasting, because if you use lagged thirds of the time series, you get the data from the client A could get the data from client B, because it's a time series and you are working with lagged values. So from this point of view, vertical federated learning, it's a little bit more challenging because we are combining different features of data. And there is some good examples where vertical federated learning can actually bring a lot of value. One is renewable energy forecasting. I will give more details, and this will be analyzed more in detail later. But one benefit is that you can actually improve renewable energy forecasting skill by combining data from different geographically distributed sites. Can be solar, can be wind, or even by combining data from other sources like satellite images and sky cameras. And some years ago, we published this paper where we show that there is a clear benefit. You see here an improvement of forecast error for all the lead times of combining data from different owners. And these different owners are, in this case, they were wind farms geographically distributed across the region. So here we show in 2017 already a benefit from exploring this information. Another example, and in a different domain, not on forecasting, is on asset condition assessment. So here we are interested to know if the condition of a transformer is good, fair, or poor. So to make a classification of the fault. And an interesting result that we also show in this paper is that if you combine data from different utilities and data from different transformers, you can improve actually the accuracy in classifying the type of fault of those transformers in another utility. So something we showed in a real data set from the company, in this case 2 companies, X and I, is that we can predict the type of fault in the transformers of company X by just using data from another utility. And in fact, if you see here at the values, we actually improve in all the accuracy metrics, all the results. So in fact, this utility I have more data than utility X. That's why you see an improvement on accuracy, but also shows that we can have, in fact, a lot of value by using data from other utilities and other competitors. As long as, of course, we keep the confidentiality, and this is one of the big challenges. So these were two motivational examples. Now going to applications, I will cover 2 applications. The first one is renewable energy forecasting. As I said, there is a lot of value in combining data from different owners. Just to give an example, imagine that we have different PV power plants, each one with their set of measurements, power measurements. We can combine them in a vector autoregressive model. So a simple linear regression model, but a multivariate one. So this is all the points we want to forecast. And these are the lagged values of all the time series we have. You have here an example. If you want to forecast just for 2 sites, note that we are forecasting the power of site 1 as a function of its past values, but also of the past values of the other site, which is a neighbor of that site. So, and this you see here already a question of confidentiality problem, because if we are forecasting 1 as a function of 1 and 2, of course that the site 1 will have access to the measurements of site 2, and this is of course in general, if they are competitors in the same market or if they are in the same region, is always a barrier to share data. And so this is the model we develop for very short term, so for hours ahead forecasting. And something we are working right now is to extend this to day ahead and days ahead, so for multiple days ahead, and we are using additive models to capture the nonlinearities, in particular in the case of wind speed, relation between wind speed and power. But most of the results we show in the beginning were just with lagged values like you have here for very short-term time horizon. Something we saw in the literature, there was some previous works where they were using alternating direction method of multipliers. And basically they were breaking this regression problem. So we have the power, we are forecasting the locations, lagged power observations of all these locations and the coefficients that you want to estimate with ADMM. So what they were doing, they were breaking the data into subgroups, and this data would be local to each of the owners. But then there is an iterative process where you do some kind of a conciliation between the matrices that are calculated from the different owners. And the problem we found, and this is in this reference, if you want to see more details, that after some iterations, it was possible to recover the original data. So there was data breaches on this method. So confidentiality was not ensured. At some point, if you know mathematics, it would be possible to get all the original data from all your competitors. So that was the main limitation. And then we started developing this new approach. We call it a protocol, a privacy preserving protocol, because in fact, this is some kind of encryption of data using algebra, together with ADMM that was already in the literature. So reminding again, we start with this, all the power measurements, lagged power measurements, and the coefficients we want to estimate. And what we do is that we make an encryption of data. And we do this encryption with algebra. And in this case, the power, it was multiplied by a combination of 3 matrices. These 3 matrices, they are only owned by each owner. So owner of data 1 only knows this matrix, 2 only knows this one, and 3 only knows this one, and only the 3 combined can give a proper encryption of the data. We do the same for the lagged power observations, in this case with a second or another type of matrix that is to encrypt the coefficients. And in this case, only there is no combination of different matrices, and only owner 1 and 2, like you see here, know this matrix. So you make an encryption and then you distribute the key, the encryption key, by all the data owners. So this is somehow bulletproof against data breaches, because no one have all the information to go back and get the original data. And then we do distributed computation like ADMM. So we train the models locally, we unencrypted data. So in the end, we get encrypted coefficients, and then with the matrix that only the owners have, they can unencrypt and going back to the original coefficients if the data was not encrypted. So the solution we get here in terms of coefficients is exactly the solution we get here without encrypted data. So we don't lose any accuracy by doing these operations and these algebraic operations. And that is, in our opinion, a big advantage of this method. I show here some examples. This is something we still are working. This is an example of the accuracy for 13 wind farms located in France, and we are doing this for 48 hours ahead. and you have here a zoom for the first 6 hours. And we are comparing basically 3 models. One is an autoregressive additive model, so we include here nonlinear relations, and then the vector autoregressive that combines all the information from all the wind farms in a single model. So the idea here is that it's able to capture spatial temporal correlations, which is a big advantage. And finally, gradient boosting trees, which is a state-of-the-art machine learning that uses the same input data as VAR. The only difference is that it doesn't guarantee any privacy, and it's not distributed. So even in terms of computational time, it requires much more computational time. Looking at these results, we see that our VAR approach, so when we combine all the spatial temporal information, it outperforms an autoregressive, which is an univariate model, just with the data from the model. It's from that site, we don't combine from the neighbors. And we see we have an accuracy that on average, it's competitive to gradient boosting trees, but for horizons greater than 6, they are gradient boosting on average is better. Of course, on the 13 wind farms and on the 60 wind turbines, in several cases, gradient boosting is also outperformed, but on average, it has a good performance after 6 hours. Before 6 hours is worse. So this is an ongoing work. Our goal is to have the same performance of gradient boosting, because I want to underline that one of the advantages we have here is that we are able to handle private data, and this is a big advantage. So in terms of outcome, we produce this privacy-preserving protocol that is also able to have 2 different communication configurations. We can have a centralized model where we have a node that concentrates all the information from the data owners, or we can have a full peer-to-peer where there is no central node and everyone exchanges information with everyone. This one you have to exchange more data, but it's more robust to failures of communication. You see here, this is a reference for the paper where we published this approach, and this was also a patent we submitted to European Patent Office because we believe this can also be applied to other domains, which is exactly what I will present in the next slides. So this was our main outcome. We started in forecasting, and then we started to apply this to low voltage control. So the next step was to use this privacy preserving protocol that we developed, and then to apply this to low voltage control, and we'll explain in the next slides how we made that. Just to give an idea and the context to this, so there is some challenges in the operation of low voltage grids. We have a lot of resources that are emerging in the case of electric vehicles, small scale PV, battery storage, and at some point the low voltage grid are like a major bottleneck for the integration of distributed energy resources. If we want to increase more PV at the low voltage grid, we start to see a lot of problems. There is a very well-known case of Australia that have a very high integration of PV in low voltage grids, and then a lot of technical challenges on the low voltage grid. And there is some real world challenges. One is that there is a lack of accurate information about grid topology and parameters. So either you don't have the grid parameters like the impedance of the lines, or you have them, but they are not accurate or they are not updated. Sometimes even the topology is not updated. Sometimes even the topology is not known on low voltage grids. And this is what we develop is exactly for a scenario where there is this lack of information or information is incomplete. And then there is this question of real-time monitoring. But then I redirect you for our webinar number 5, where you see a presentation about this for the data-driven state estimation. So what we are doing here is to explore a known relation, a linear relation between the voltage and active power on low voltage grid. And so the question is, can we express this relation as this relation between active power and voltage as a sensitivity factor so that we can embed this in optimization? You have this reference, and in this reference, they show that this is possible. So by making a linear regression between voltage and active power, we can get or extract the coefficients of the regression, our sensitivity coefficients for the low voltage grid. And that information is quite valuable to make a control or to solve voltage problems. And so if we follow that, we'll have something like this, where you have a numeric value that give us the impact if I make any kind of active power control, I increase or decrease in one node, I know the impact on the voltages in the other nodes. But one problem is that we know that these sensitivity indices, they change with operating conditions of the grid. And so they work well for one specific operating point. If we have different operating points, different loads of the power transformer, different generations on the low voltage grid, they change with operating point. So what we made is that instead of having one value, we have a function. So we have a function that tells us the variation of the sensitivity index as a function of a variable that explains the operating conditions of the grid. And so we have our sensitivity factors. They are conditioned by external variables. And the way to do this is to move from a simple linear regression, I was saying before, to a variant coefficient linear model, where the coefficients you see here, they change with an external variable or an exogenous variable that can be fitted locally as a polynomial around several fitting points. So I skip the details, the mathematical details about this, but this is already established and a known concept in the literature, and we are using as an exogenous variables the load of the transformer or the voltage on the transformer. So it means that our sensitivity indices, they change as the load of the transformer changes or the voltage of the transformer changes. So this is the model we constructed. So instead of having this matrix of sensitivity indices, we have a matrix of functions of the sensitivity indices. And yet there is this problem. So smart meter data is private data. So we are constructing all this knowledge, assuming that we could combine smart meter data or metering data from all the consumers, and we know this might be a problem in some legal frameworks where smart meter is a personal data and cannot be used for this purpose. And for that, the ideas and what we have been using is we use our privacy preserving protocol that I have showed for the forecasting. We apply it here for this model. In fact, we have these two different configurations. We have the DSO operating as a central node, so concentrating this information, encrypted information that we exchange. In some cases, when we have communities and we don't have the DSO in those communities, they want to do their own management of the PV generation. They inject and keep voltages within the limits. We can have a peer-to-peer approach where there is no DSO, and they exchange this encrypted data between them all the time. So these are some of the different configurations that are possible with this privacy preserving protocol. Just to give you some ideas in terms of results, one thing is the accuracy of the linear model. So we have used these 33 nodes from low voltage grid, and we have measured the accuracy in terms of estimation of voltage after some changes in the active power in several nodes at the same time. And you see that this was the initial voltage, and you see the voltage estimated with the power flow and voltage estimated with the sensitivity indices, and you can see this is very, very accurate. So this linear approximation is in fact a good model, and in this plot you see the difference between using a constant sensitivity model and using our conditional model, and you see that our conditional model is always better than the constant model. Of course, there is a parameter to tune, which is a number of nearest neighbors we consider, and only for some extreme values we get a poor result. So this conditional model improves even more the results and actually can capture very accurately the operation of the low voltage grid. And finally, you integrated this in a low voltage control just to see if this could be can give good results in terms of voltage control. You have here the formulation, but just to underline, we include the sensitivity indices directly in the mathematical formulation of the optimization problem to solve voltage problems. And you see here an example of these results, and we see some voltages that are above the limit. They are corrected by activating active power in nodes, sometimes upward, sometimes downward. And we can also include constraints like the balance, maximum imbalance between the phases on the low voltage grid. In this case, we constrain it to 2%, which also leads to some changes like you see here on this red line more on the voltage. So these are just one of potential use of these sensitivity indices. In fact, they can be easily integrated in optimization problem for voltage control. And to conclude my presentation, there is an ongoing trend in Europe on data sharing, and it is emerging several initiatives at European level on data sharing and federated learning. I put here these two. One is Gaia X that is being implemented in several countries, and it has a federated architecture, so it fits very well with what I was showing. And from the European Commission, the Common European Data Spaces, which is somehow also a data lake where you exchange data or you share data between different sectors, which is something, and even between different countries, we can push forward the energy sector because it can get access to information from the other sectors that is quite valuable. But however, there is, I think, two main barriers. One is that the maturity level of federated learning and data sharing incentives, it remains very low. There is a lot of research activities, but we are very far from something that can be used at the commercial level. And then there is a lack of business cases and incentives for data sharing. So making these platforms, these digital platforms, it's possible from a technological point of view, but it's very insufficient if we don't have these mechanisms like the ones that Pierre will show. And there is examples in the past. For example, the city of Copenhagen had a data market some years ago that it's no longer operating, in fact, because this second part of these business cases incentives, they were missing. So this is a big challenge for the future. Okay, and I end here just to acknowledge Carla Gonçalves and Gil Sampaio. So they were also Carla was my former PhD student, and part of this work is from her thesis, and the same with Gil. Part of the work is from his thesis, and this was made in the framework of these two European projects: Smart for RES on forecasting and Universal for the grid control part. Thank you.
Thank you, Ricardo. I would appreciate if you could stop sharing. Thank you very much for your extremely interesting and challenging presentation. And I will open in some minutes a space to answer some questions. At least we have some questions in the Q&A bulletin. And but I encourage participants, the audience, to write some other questions. Later, at the end of the presentation of Professor Pierre Panson, we will also open another space for questions. Now, Ricardo, there's a curious anonymous attendee. I'm sorry, I could not see the name, but I believe it's because of the registration in the Zoom platform process. But there is an interesting person asking this question. How are the keys distributed? Are you using a kind of public cryptography? So this is how he wrote the question. So Ricardo, please give us a clear, straight answer.
Yeah,
not an encrypted answer, please.
Yeah, we are not doing, well, we call it cryptography, but we are not doing cryptography as a technique. So it's algebra, purely algebra. So we generate those matrices. They are generated randomly by the data owners. They are not shared by the data owners. They are just combined. So there is nothing public. So only the data owners own a part of the key. And we are just doing algebra, not using these well-known cryptography techniques, because something we also analyzed in another paper is that they are, in general, they are computationally very consuming, time-consuming, and in some cases they are not robust, because, and also important to underline this, we want to have the same solution if we were not encrypting any data. So it should be the exact solution, and not like a trade-off between encryption and accuracy. So we are not doing that. So that's something we wanted to avoid.
Ricardo, let me clarify on this. Is there anyone in your methodology, anyone that at any point of the process, anyone that has access to the in your example were three to the matrices, or each matrix is generated locally and no one can have, there's no central organism generating and shipping the matrices to the users?
It's generated locally. They are combined, but they are combined in a way that you cannot get back the matrix. Something we analyzed these on the other methods in the state of the art, and in those other methods in the state of the art, after some iterations, the mathematical operations would be possible to retrieve those matrices. It is not our case. So our case is, let's say, bulletproof to mathematicians willing to extract original data.
Okay, bulletproof. Okay, that dramatic labeling of your technique, bulletproof. Very well. And then we have some more questions. Let's go forward quickly. And there's two or three comments in the chat. I would advise the audience to write on the Q&A and not on the chat, but I'll try to see what's on the chat there. But continue. Our friend, anonymous attendee friend, asked also, did the GBT model also operate on encrypted data?
No, only with the original data. So GBT, they improve, they are more accurate than the VAR model we are using. But they don't guarantee any privacy. So we are combining all the data with a lot of confidentiality breaches. Something I would also like to underline is that of course, we are losing in terms of accuracy to GBT, but there is a lot of work ahead and a lot of potential to improvement. Good.
And now from Robert Meath, I don't know if I'm pronouncing this correctly. I hope you'll forgive me. For the collaborative learning for wind power forecasting, what are the features that are being shared by the individual wind farms? Are they really that privacy sensitive?
Yeah, we are sharing power measurements. So the answer is yes. In general, between competitors, if you have 10 wind farms, they have different owners. They don't share data between them for several reasons, because they might even be competitors in the electricity market, so they would know how much the other is generating. So power measurements, in general, they are considered confidential data. In the case of wind, in the case of PV, you might also have the same thing.
Okay. Ricardo, in the interest of time, I would recall you that we need to give very short answers, please, because we have many questions. Congratulations, a lot of interest.
Okay, I'll be more fast.
Amir Hossein Ahmadi asked, I am curious about why you use vertical federated learning and not transfer learning or horizontal learning.
Well, horizontal learning, in this case, it doesn't make sense because we want is to combine features, not records. There is other applications, not this one. Transfer learning, the same. We want to have the model as more accurate as possible and using data from the wind farm. So transfer learning will not work on these problems.
Very well.
Okay, there was another question.
I'm jumping to answer other questions from other people. So Elaine Agua asked, is the encryption method proposed compared with the differential privacy preserving methods applied to the original matrices?
Now we compare this with differential privacy, but in differential privacy, you have to trade off accuracy and encryption. So we have shown that if you do that, you might have a model that is robust to privacy, but with a poor performance in terms of forecasting results.
Okay. Gay Luz asked, in one of the plots, there was a parameter about the nearest neighbors. Mm-hmm. Does that mean that we can tune the peer-to-peer privacy model to a fully distributed in which modes only talk with its neighbors? What are the impacts of topology on system performance?
Okay, it's not related. The nearest neighbor that was there was just for the local linear models. So for the varying coefficient models, when you do that, you have to select a set of neighbors and they are weighted. So you fit a local weighted linear model around the neighborhood, and that was the parameter. In terms of structure for the peer-to-peer, we didn't explore that, but yes, it might be possible to optimize the structure for data exchange so that we minimize the number of edges on the peer-to-peer. We have not explored that, but it's a topic for future work.
Okay, running because of time. Matthias Berger asked, in the wind power output forecasting example that you mentioned, how were these wind farms geographically distributed? More specifically, how far were they from each other? And did you compute correlation coefficients between their time series? More generally, in your experience, how much correlation or dependency, good, correct, better to say dependency than correlation, between random variables do you need to have for federated learning to make sense? Yes, and I would add to this question also the following reasoning. Putting together several wind farms only makes sense if there is mutual information shared. If there is no mutual information, it cannot improve the model. That is basic. How do you detect? So the question is how you detect if there is mutual information between wind farms.
Okay, so there is more than one question. So going to the first one, so they were, I don't know now how much kilometers they are far from each other, but they are far. So some wind farms have a distance of 50, 60 kilometers, sometimes even more than 100 kilometers in France. We use a lasso penalty. I didn't mention that, but we use a lasso penalty, different variants of lasso, so that you can automatically find these cross correlations or cross dependencies between the wind farms. And we have applied these to all the Vestas wind turbines in Scandinavia, for example. So you see the size of how far you can find relations. Of course, in the end, you have some small clusters, or instead of having a big cluster, you have small clusters of cross correlations between the wind farms. But I would say it's very difficult to say if you do this in 1,000 square meters or 2,000. There is not a rule for that. What we use is lasso because automatically it finds that. So you need an automatic method.
I am sorry, I need to run. Otherwise, Pierre will be tired of waiting, but he will forgive me. I have still from Samrat Asharia. Do you create privacy matrices for each lag time?
Yes, we have to encrypt all the lag times. So you have that matrix M. It's for all the lags.
Okay, still from Amir Hossein Ahmadi, what algorithm did you use in the aggregator?
I think the aggregator you mentioned was my initial slide with the federated learning. So we didn't make that. That was an example of what is being done by other groups with neural networks. There is different variants. One, as far as I know, is just a combination of the weights from the neural networks trained on the different data.
Okay.
But was not the focus in our case.
It would be unfair to leave one question unanswered. So from our anonymous attendee, what is the difference between your approach and using something like homomorphic encryption?
Our approach is algebra, pure algebra, simple matrix calculations, of course, with some, not secrets, but with some particular calculations. But more than that, we get the same, I want to underline this again, the same coefficients if we were solving or fitting the model without any concern about the privacy of the data. So, and we don't lose accuracy on the method. So.
Okay, so if I forgot to put forward one question from the audience, please forgive me. But I think we depleted the Q&A bin. And so we now thanking Ricardo for his presentation. If we were in a live audience, we would clap our hands, okay? But it's a bit funny to do that here. So we will move forward to another presentation. This time, allow me to share again my screen. This time from Professor Pierre Panson. And here you have him smiling in the bad weather of Denmark, I suppose, I'm not sure. Pierre Panson is an IEEE fellow, and he is a professor at the DTU, the Technical University of Denmark. And as an IEEE fellow, he, of course, has a very sound, robust number of publications that have been recognized, but he's also editor-in-chief at the International Journal of Forecasting. And forecasting is exactly one of the things that he stands above other colleagues in the world. And I can say that I myself had a very successful exercise in forecasting, because when I first met Pierre Panson, I forecasted that he would be a bright scientist. It was easy. It was easy. I'm sorry to say, unfortunately, it was very easy to say that. Nevertheless, his research interests, as you know, and for those that don't know personally, Pierre Panson have guessed, his research interests orbit around forecasting, optimization, and game theory applied to power systems. So we will give the screen to Pierre. You can share and start your presentations right now. Thank you very much.
Thanks for the very nice introduction. That was very kind of you. My idea today, so yeah, this is, I'm not employed by INESC TEC in Porto. It's the slides we have for the introduction. What I want to discuss today, so first, I mean, Ricardo gave a very nice presentation and gave you a very good introduction and very advanced topics within this point of collaborative analytics. And he mentioned a few times, you know, that we need incentives. So I want to discuss here the point of incentives. And in some works, actually, we have also been connected with Ricardo and some of his colleagues on this topic. But here it's specifically some joint work that we did with Li Yang, Han, and Jalal Kazempour at DTU that I'm going to present. But really, I mean, these works are linked to what was done by Carla. So Carla Gonçalves was mentioned already by Ricardo. She did some work in this area. And then, yeah, we are doing that in the frame of some EU projects that I have to say thank you for. And the paper is available online on archive. So you can go look at the wallpaper. Here, it's really selected the material and also a more general picture of what we want to do. So the thing here, and I was a bit surprised that you didn't ask this question to Ricardo, is for me another question related to energy data is how valuable is this energy data anyway? Because maybe here we're making a big deal, you know, sure, we could be more efficient, sure, we could be more optimal if there's some data sharing, but maybe data is not that valuable anyway. And I think it is an open question. We don't have the answer. There are indications out there that data is becoming more and more valuable in so many areas. I think health is really clear. You have all this smartwatch data, or, you know, personal data that can be very, very valuable. That's clear. In energy systems, it's unclear. But if we want to reveal the value of this data and answer this question, actually, we first need to design these new mechanisms so as to reveal the value of data. So for us, it is something that is a very nice question, I think, as a challenge to contribute to the field. But I have, talking about making a prediction, my prediction is here at the bottom of this slide. We've been working for quite some time, you know, with renewable energy in markets, and we always complain that the value of energy, or, you know, the price of energy in markets, as we have more and more renewables, is going to get lower. But the value of data is increasing, right? So that means at some point, the value of data might actually be higher than the value of the energy itself. So maybe it's true, maybe it's not. But if that is the case, then we have to start thinking, what would be the right market mechanisms so that we properly value both data and energy. And I think that's where we are going with different groups focusing on this field. So I want to give you a motivating real-world example that I think is the right sandbox to ask ourselves this question. Then I'll discuss alternative approaches to corroborative and market-based analytics, and I think I'll go quite quick because Ricardo gave us some good things already. And then we'll zoom in on these regression markets. All right? Good. So let's go. So a motivating example that quite a number of us have been through is this problem of participation of renewable energy producer in electricity market. And here I say wind farms, but it could be solar power plants. And so typically wind farms, they offer an electricity market based on their forecast. And to obtain this forecast, they use their private information, maybe some public information. Maybe they give that actually to some forecaster, a company, and they pay to have a tailored forecast for the wind farm. The thing is that in the electricity market, the forecasts serve as bid or tweak of the forecast. And these bids are placed in advance, obviously, they're based on forecast. Any kind of lack of forecast accuracy would lead to a loss of revenue. There's a penalization that comes there, which is due to the spread between the day-ahead market prices and the balancing prices or the real-time prices. So all these wind farms, we believe they have an incentive to have the highest forecast accuracy as possible. That's where they would get their best revenue, their optimal revenue. Ricardo mentioned there's quite a number of studies that show that if you use data, from neighboring sites, data, that are kind of related from weather station, maybe some remote sensing, etc., that are in a neighborhood. If you use data from your competitors, maybe you can improve your forecast. But as of today, if you think of incentives, there's no really incentive to do so. And if you ask different companies, they say, actually, even if they were incentive, we would play bounded rational and we would not want to share, right? So we have to find a way to incentivize and maybe also, make all these agents in the system a bit more relaxed about this idea of data sharing. How we want to do that, we have to design a framework. So here it's a regression framework I want to discuss because it's specifically about forecasting, but there's different type of analytics framework that I will discuss that we'd like to develop. And we want to design this framework so that we allow the agents to collaborate and all should benefit from it. So that's where the mechanism design angle comes in, because you really have to design a mechanism that has the right properties. So here, typically with this example, imagine wind farm B in the middle, trying to improve forecast accuracy, could do some kind of federated learning with wind farm A. So that's what Ricardo mentioned before. And wind farm B could pay wind farm A for that. But then wind farm B could directly buy data from wind farm C because it is known this data could be very valuable to improve forecast, also against remuneration. So in this case, wind farm B gets better forecasts and so a higher revenue from the market. Wind farm A gets an extra revenue from wind farm B, so is better off. And wind farm C, the same, gets a better revenue from wind farm B, so is better off. If the mechanism is well designed, everybody is truly better off. And actually, the electricity market as a whole is also better off because we make more optimal use of the information out there, right? So that sounds like a win-win situation. But how are we going to do that? Ricardo was mentioning one approach that has been pushed really forward by Google. It's been, 5 years now? It's 5-6 years that Google has been pushing forward federated learning. And that would be one approach to do it. But there are many approaches that could be considered. And actually, they are out there already, these different approaches. In all cases, you see here the alternative approaches. We really foresee, and again, Ricardo, I think, was going towards that with his last slide about EU and Gaia, etc. We really see that there are going to be analytics platforms that will be there to support this kind of collaborative and market-based analytics. And then there can be different flavors of how you can post a problem, and ask others to help and remunerate others maybe. So these are three major scenarios that I have here. And in all cases, we have this central agent, which is the agent that posts the task and try to improve the solving of this task. And then the support agent, they're those who have data or information that's valuable and that are ready to help, right? In the first case, collaborative analytics is really the vanilla version of federated learning. We do this decomposing of the analytics task, and then there's this iteration between the central agent and the support agent to better solve the task. And we can have a privacy preserving layer. But as I was saying, it's a vanilla version because there's no incentive. Some of the support agents are altruistic, and they do it to help. And maybe you could think, it's kind of an exchange contract. They're going to take turn being central agent and helping each other. So maybe they believe they're all going to benefit, but it's not really sure, right? The second angle, Ricardo mentioned the data market for Copenhagen, and there are other data markets, right? A central agent could directly buy data from support agents, and then there's a payment versus the data. And if we use differential privacy, it doesn't have to be the data directly that's been sold. It can be, a noisy version of the data. It can be also some filtered version of the data. It can be, I don't know, you can multiply also some of your features. So it can be some kind of tweaked version of your original data. But still, the idea is that the support agent sells something that may be valuable to the central agent. And there are different types of data markets today that are being designed in this direction. But really, the end game is to have some general version of this, where you could combine distributed computation, data sharing, remuneration or not, privacy preserving layer, etc. And I think that's where federated learning is going towards, and other people also coming from different angles are also going in this direction. And we see a different version out there. I think Ricardo was saying, that we don't have so many business cases. Actually, there are quite a few very strong business cases lately. So in health application, there's this company Orkin, which is based in France and the US, that raised a lot of money. They just got $200 million more from Sanofi in France a month ago, I think it was. To develop these kind of ideas so that, we further develop this type of platform so as to better solve some tasks, so related to health application here, for example, but while respecting that the data is being distributed and the agents have heterogeneous views on their willingness to share. So I think it is happening, and it's going to happen very fast and very strong. So now let's zoom in the data market, the regression market, sorry. And we're going to consider a case where we have a central agent that I call forecaster. And forecaster uses a regression problem as a basis to predict renewable power generation. So it's pretty much what Ricardo showed at some point on the slide. And here forecaster owns a set of features. So I think I can go a bit quick here. We have a model based on the features to model the connection with the response variable. And to make it simple here, I keep the model linear. You have it in the middle here. So I want to fit this model. I'm going to use a convex loss function. It can be a quadratic if it's a least square fit. It can be a pinball loss if it's for quantile, etc. But as long as it's convex, it works nicely. So based on the data and the fitting, we have a minimum loss function value, which is S little omega star. So that's the value of at the fit. Okay. But now forecaster could say, okay, I want to post this regression task on analytics platform, and I want to improve the model fit. So forecaster is going to declare willingness to pay. So here it's a €1 per percent point improvement in the loss function S and per data point provided, because we want to have a volumetric component to it. So what happens then? On this analytics platform, there are two support agents that I call here good data and useful features. Each of them have one feature, Z1 and Z2, and they want to be remunerated for it. We have this regression problem that I showed before. We augment it to have these two features. It's a linear model, so it's very simple. We just have two more terms with coefficients, and it's still linear. We then have an augmented vector of coefficients that is written beta plus here, and we can fit it in the same way. We use the same convex loss function, and then at the fit, we're going to have the coefficient, and we have the value of the objective function at the fit, which is written here S star big omega, all right? And if the features are variable, we expect S star big omega to be less than S star small omega. Otherwise, we could have done that through some cross validation exercise. That means that these features are not valuable and we don't want them, right? So if we keep some feature, most likely they're valuable and we have a best fit. Okay, but now I said we want some incentives. So we want a market. We need revenues and payments. It is actually quite straightforward, and there were a few proposals out there that we generalized. Here for forecaster, the payment is again straightforward. Forecaster declared a willingness to pay, which is per percent point improvement in the loss function and per data point. So the payment is given here at the top by this willingness to pay times the improvement in the fit and times the quantity of data. Okay, but now this payment has to be shared among the support agents. And that's where we can use also this recent tool from machine learning, Shapley additive explanation, because then we can say really, you know, this feature is responsible for, let's say, 40% of the improvement in the fit, and this other feature is responsible for 60%, right? And Shapley additive explanation have all the nice properties, or some tweaked version of it, have all the nice properties so that we have a proper allocation mechanism, okay? So if we use this idea, what we get actually a market that has a wealth of good properties. It's going to be budget balanced because of the properties of the Shapley explanation. So the sum of the revenue is equal to the sum of payments. We have symmetry or anonymity. So that means that even though you would switch the labels of your agents, they would still be treated the same. We have a zero element. So that means that if you come with a feature that has no value, you get no payment. And then we have incentive compatibility and individual rationality. So you incentivize to tell the truth, so to give your best data, otherwise you would lower your revenue. And it's incentive compatible in the sense that when you go into this mechanism, in the worst case, you get zero, in the best case, you get the revenue, right? So that sounds very nice. And this is for a very simplistic version here with a linear regression setup, but we can generalize that to non-linear regression, to a wealth of convex loss functions, etc. Okay, but most importantly, we can generalize it to a real forecasting setup, because here I only showed you a fit, and fitting a model is not what we care about. You know, we're going to use this model afterwards for forecasting. We may fit this model batch or online, right? So can we use this concept? Yes, actually, we can use them readily. In an online regression markets, we have shown in the paper that we can generalize the type of payment that were proposed with some what's called like sliding estimates of the Shapley additive explanation, but with the same kind of payment rules and revenue rules. And it's the same when we go out of sample. Actually, for each and every forecast that I issued, based on the new data for these features, we can also use Shapley additive explanation and this kind of payment rules to decide how we're going to define revenues and payments. So actually, with this kind of basic idea, we can have a market for batch, online, and out of sample regression market. So for learning and for genuine forecasting. Okay, so quickly, I want to give you a real world example. It's not 100% real world because the data is coming from this wind and solar integration studies in the US. So, you know, it's coming out of models, the weather data, and then they transform it into some power data. So that's why there might be stronger correlations than with real data. But we have wind power generation for 9 locations in South Carolina here, and 7 years of data with hourly resolution. So you have the locations here, and the data can be shared anyway if you want to reproduce the work. For simplicity, we do 1 hour ahead forecasting using some type of VAR models, like Ricardo was mentioning. And then all these wind farms take the role of central agent and support agent for each other. So we have a full market here, full data market for all agents to help each other. So what's happening is that we can define a task. So here I define the task as being online quantile regression. So we learn as the data is streaming. For a given quantile that can be set by the agents, you know, they believe that's the best bid in the market, for instance. And then we use cross-validation to decide the number of lags. Okay, so 2 lags for the all data of the central agent and 1 lag for the other agent. And then we have these 2 willingness to pay that are defined for in sample, so training, learning, and out of sample, so for genuine forecasting. Here you see an example with these plots. It's the cumulative revenue as time goes. You know, we start from 0 because the data starts streaming, you know, there's no revenue. And as data is streaming, we apply all these revenue and payment rules, and then the revenue grows, right? So on the left, it's from the training, from the online regression market. And on the right, it's from the genuine forecasting. It's the out of sample regression market. And so eventually, it's my last slide. This is what happened after a few years. You know, we have this bar plots that show some revenues for the different agents. So if you look at each bar, you see at the bottom here on the left, there's written A1, A2, A3, etc. So that's the revenue of A1 that comes from the payment of others. And the plot on the left, the bar plot, is for the training side, and the right plot is for the out of sample forecasting side. So you see, for instance, for the first bar on the left, A1 is not paying itself, right? So there's no reddish block at the top of this bar, but then this reddish block is on the other bars, right? What we can see is that these different agents seem to receive very different payments, very different revenues from the others. The overall revenue is very different, but also the quantity of money coming from others is very different. And it's really linked to actually how valuable this data is in training the models, the regression models, but also for the genuine forecasting. And eventually, at the end of the day, it's in the paper, you can look at it. We can actually even deduce what is the value per data point collected of each and every agent in this market. So it's very interesting to actually have the answer. I was telling you at the very beginning of this talk, what's the value of the data points I collect, okay? Good. But so to finalize, to close this talk, actually, I'm going to close also based on what Ricardo was saying, because I think the two talks are highly connected. I think this field has a very bright future, and actually, I think it has a very bright future for energy applications. There's so many business cases that we can consider, but there's also the need for many methodological developments. We have quite a few collaboration on that. So with Ricardo, there are some people working on that also in the US, in the UK, etc. I think it's a very exciting field to be in right now. Obviously, there's this point of privacy that was discussed quite a bit before, but there's also this point of competition. Here we say we have a market for data, but then it's going to be connected to a market for energy. So we have to make sure that these two markets together coexist in a nice way. Otherwise, we don't want to, have some kind of distortion or having some kind of problem, for instance, due to spitefulness, because we would connect these two markets. Finally, there might be some ethics issues, but I'm not here to discuss that today. So thank you very much. And I'm obviously open for questions if you like.
Thank you so much, Pierre. Merci bien.
My pleasure.
We appreciate very much that you took the time to be with us. And this is one of the very good examples of positive things that happen when we support cooperation. The mutual enrichment of research groups and people from cooperation is absolutely fantastic, but also human relations and friendship derive. And of course, our audience noticed that several papers were written in common by you and Ricardo, and of course, and Carla, and of course, I will say, and of course, other members of your teams. So it's a nice thing to see, because we were talking about competition, but cooperation is also a very good thing. And actually, both your talks addressed in some way competition and cooperation, showing that they are not mutually exclusive, excluded. They are not, so it is a very nice arrangement of talks that we have today.
Can I comment?
Yes, please do.
Very, very quickly, because this discussion has been also there the last few years when people have discussed this peer-to-peer markets for energy and community-based market. I think our role, we are not here to say, we have to compete or to collaborate. So it's the same for our research, but also for what we do. I think we're here to propose different options. So I think Ricardo did it very well to say, we can have it in a centralized way, we can have it in a peer-to-peer way. And here's the same, we can have it in a competitive environment, but we can also make it a collaborative thing, right? So we're here to propose these different options, and then, I don't know, regulators or industry will decide what they prefer.
Very good. So now we with our small talk, we allowed the time for people to ask questions. So we can see now, start with Nitin and then Shrivastava. Would there be a dedicated system operator for regression markets? That was his question.
So that's a very good question. And again, it links to what I just said before and Ricardo's talk. Is that we could consider different scenarios. If we wanted to make it very peer-to-peer, you would expect that there's no a central agent, like really in the sense of operating the platform, but maybe there will be one. The same way, you know, for energy markets today, we have someone who manages the market, and at the end of the day, it's a software company. You know, they provide a platform, they make sure this platform complies with the rules set by the regulators, and the agents are well treated. But yeah, I mean, different options are possible.
Well, thank you, Pierre. Now, Amir Hossein Ahmadi asked something that I need to give an interpretation to his sentence. He says, I think the earning will be end after the forecasting accuracy stop improving, right? So yes. What will incentivize customers to share data?
So Amir Hossein has a very good comment. And I told you that's why we have a volumetric component, because we want to incentivize both contributing to some kind of accuracy in some estimation of forecasting, but also to say thank you because you continue maintaining it with some new data points, right? In an online environment, this accuracy in a non-stationary environment, this accuracy is not for granted. So you could always make it evolve as you have new data. So by having this payment that consider both the volume, so the fact there's new data point, and the contribution to accuracy, you actually solve this problem.
Well, then Samrat Asharia asked, and he is threatening. First question, let's see how many he's going to ask. First question, I believe a central agent also becomes a support agent.
Yeah.
And vice versa. How are you managing this transfer?
Yeah. So, I mean, here, the thing is that in terms of mechanism design, if we make the system efficient and fair, whoever has the hat of central and support agent, somehow it's not going to create problems where the exchange has, right? So that's how we handle this problem. But I know Ricardo, he could not present it today. He also has a view of how you would make it a multiple buyer, multiple seller setup. And then you would also naturally control this issue of, you know, having different hats in the game. Well,
and his second question, I mean, he says second question, but he has 4 more. So let's see. Second question, I'm going to tell them all. How are you paying for the data? Is it for each sample or for a batch of featured data? If you pay per sample, how would you ensure that the data sample obtained at T equal to at first time step will also be available at the second time step?
Yeah. But so the thing is, eventually, I want to see it in an online environment. So the data is streaming. And when you're in an online environment, you know, you have some kind of memory. So you don't need to keep the old data. You can always use the new data, update your memory, and continue like that, right? So in practice with this setup, this application, we don't assume you want to store data eventually. And there's a payment per data point. Every time streaming, you know, every time a data point is shared, there's a payment.
Okay. Now, Matthias Berger asks, could you clarify how revenue payments were computed in the South Carolina example that you discussed? From the perspective of one agent, was he or she able to make payments to others because the revenue from day ahead balancing markets improved as a result of improved forecasting? Thank you.
Yes. Yeah, but so let's clarify this example, you know. So if you say the agent in the market, say my optimal, my best forecast that I can put on the market is the quantile with a certain level, right? So now I know anyway, that's what's going to bring me my best revenue. And if I have the best forecast for this quantile, it's also going to be my very best revenue, right? So you ask the data from others to improve that. Then you have a loss function, which is this quantile loss, that you can calculate if you were to have your model alone or if you were to use the feature of others. So that's this point of Shapley, right? So eventually you can say, now that I make this kind of money, I know it's like 50% because of me, my own feature, then 10% because of Ricardo's feature, and then 40% because of Vladimir's feature, right? Then the agent has declared the willingness to pay, saying, you know, I'm ready to share a part of my revenue, and we'll do it fairly based on the Shapley additive explanation. So if my share, for instance, I say it's $1 every time for every hour, then I will give, I was saying 10% to Ricardo and 40% to Vladimir to say thank you for your contribution. Okay, so that's how the payment is made, and then we do it every time we make a forecast and we bid in the market.
Okay. Matthias also asked a clarification on your example. Over how many weeks or months or a year were revenues computed?
I think it was 6 years. I forgot exactly the timeline, but it's six years. So I mean, the willingness to pay numbers are made up by me. Yeah? So I cannot tell you that's the money you would make. It's an example, right? It's actually some work I think we agreed with Ricardo we need to do. After, we have to be able to design the mathematical machinery so that people decide on their willingness to pay. You know, how much are you ready to pay to improve your forecast in a market, or when you do, I don't know, voltage control or whatever.
Okay, now I'll clump together two questions from two people, Nitin Anand Srivastava and Robert Meath. Do you think data and energy markets will coexist in the future, or may the data market dominate because the energy market will be fairly algorithmic or automated? And that clumps together with a question from Nitin that was saying, what are your views about the market power? So you can answer this together.
So thanks for the question. It's a very good question. You know, when we first asked for funding for this topic, it was with my colleague Jalal Kazempour. We wanted to directly design markets peer-to-peer for data and energy. And again, because for us, the question is that how do we design that? And then as we design it, we could realize, you know, that one is going to take over or maybe not, right? But as long as we don't have a common market for that, I cannot answer this question. I made this kind of prediction in my second slide saying, I think eventually the value of data will be more important than that of energy, but I might be wrong, right? So I think we need to think of these two markets together, and then we cannot decide. We will just see which one will take over eventually.
Well, Amir Hossein Ahmadi asked if you consider edge computing for managing the big data, or do you have any other technique to deal with big data?
Yeah, so it's not stuff I do myself. I confess I'm not the most advanced expert in edge computing, but I know some of our colleagues from Aalborg, for instance, Peter Popovsky and some others. They are looking at different scenarios on how you could use edge computing for this kind of market. So yes, it makes total sense.
Okay, and finally, the last question begins with a sentence that I would like to use it myself. Thank you for the interesting talk.
Thanks.
And then there is a question. For the regression markets, I mean, Saurabh, our audience member, I was wondering how sensitive the value of each data point depends on the chosen forecast model. If this is the case, is there a way to ensure that the forecast model is chosen in a fair way?
Yeah, so this is a very, very good question. And that's where we have a limitation of this kind of ideas, is that here it is obviously conditional or given the model that has been posted, right? So if I'm a central agent, and I'm very silly, I'm saying I want to have a very simple linear regression model, but actually the value of Vladimir and Ricardo's feature is only revealed if you have a nice nonlinear model, right? Actually, in a way, I will underpay because I will undervalue their features. But it's my problem because then I don't get the full value I could have gotten from them, right? So you would actually expect that people would have an incentive to try to be as smart as possible, to maybe not post a model, but actually post a family of models. And then the platform will, I think that's the proposal of DALE that we worked on actually with Ricardo and Carla originally. They say, you know, maybe the platform, that's the job of this analytics platform, to actually go over the class of models that have been proposed and then automatically select somehow the best features and their value given the best model. But it's a very good question because we don't really know how to do that. And the implications for fairness are really important.
Okay, so I have one final question for both of you. Ricardo and Pierre, which is a simple question based on the following. Encouraging data sharing will only work, in my view, if an agent that would be willing to share data would perceive that it has more to profit with sharing than without sharing. And sharing is a problem because there's also always the opinion that through sharing, the agent will give advantages to competitors.
Yeah.
So it's a matter of showing that you gain more by sharing and that your competitors do not benefit more than you yourself benefit.
Yeah.
So this is a very complex psychological problem, not only mathematics. Okay, so I would like to hear your thoughts, because this is also has links with the business decision making, so psychological factors enter here.
I'll answer very quickly. I'll let Ricardo develop on that. But as I said it earlier in my talk with bounded rationality, I've had discussions with companies where they say, just from the moment I hear that my competitor is going to benefit, I'm not happy, right?
Exactly.
And there, I agree. How do we do with that? I don't have an answer. So Ricardo, do you have an answer?
Yeah, Ricardo, I'm hoping for your answer, because one of the problems is showing that although a competitor will benefit, you'll have a personal extra benefit. That is the problem to demonstrate.
I think depends on the use case. So in some cases, like the ones I showed, you don't have to share the data. You can just engage on collaborative analytics. So you don't share data and you get some knowledge. There is two things. Actually, we have a project that will start next year that is covering those two topics. One is to include here persons from social sciences, so not just to work from the mathematical point of view, but to have someone with expertise in behavioral economics and design incentives that do not necessarily are monetary. So you can even exchange your data by being a good citizen, for example. In some use cases, this might be a driver. Another possibility is to think on barter exchange. So you share data, but you receive something in exchange. And this is the model that the apps we have on smartphones, we are using most of them for free. And in exchange, we are giving data from those apps to the provider of the service. So we are sharing data in exchange for a service. So in the future, this might be the case. So we could trade data by service, even by electricity. We were thinking we have a project for a supercomputer, a green supercomputer. So that green supercomputer can exchange computing power by more green energy from the neighbor. And so that is an example of something similar we can do for data. So we can exchange data by getting even renewable generation. And I give my data and then I get some renewable generation.
Well, you both got to my point, which is we need the research on how to provide a good marketplace for this exchange to give incentives to have data sharing. Because it will not be enough to have algorithms assuring privacy, etc. It will not be enough if the method don't address the concerns of the business people. And as Pierre also said, as an example, some people are more concerned that the competitor does not grow than concerned with his or her own growth. So this needs to be addressed. And as Ricardo correctly said, we need to include people from social sciences in these kinds of projects. Because in our experience, like for instance, in my opinion, people that put a lot of effort in theories about marginal prices, believing that they would open the way for rational organizing of things, forgot the human factors in the process. So marginal prices in many cases are not the good policy inducing indicators. Any last comment for everybody?
Yes.
Because I need
to
close the session.
There is two questions that I think we can answer them quickly.
Two new questions. Very good.
I can take the
Thomas,
first one.
Thomas, could this data sharing and the remuneration methods link in any way with the new cryptocurrencies trends?
No.
That one I can answer quickly. We have been using IOTA, and they have their own cryptocurrency to implement this. So in the end, what we have showed today, it will be leveraged by these new technologies on blockchain. So the answer is yes, it is possible. We are doing that. It was not presented here today because would need 1 more hour to show that.
Next webinar. This is a promise here. Finally, Milad, in the current paradigm, the extra benefit of sharing the data is allocated to each agent via a central mechanism. How about the situation where each agent has a private value for its data, and how should they value their data? Who would like to answer this?
I mean, can you hear me?
Yes.
Yeah,
okay. I mean, I think I said it earlier, it's difficult for the agents to actually find out what's the value for their data. And we've discussed several scenarios with my colleagues at the TU, with Ricardo, with some others. It can be privacy driven, right? So you could value how much, I'm ready to give up on some privacy for some money. And maybe it's very difficult to answer, but still it's one scenario to think of it. But we've discussed, I think it's, there's been several papers. We can also, have some people who say, okay, now I know how to put a threshold. So it's going to be, instead of just valuing the privacy or something else, it's just a threshold. If I get something out of it, I'm ready to share. If I don't get it, I'm not ready to share. And that's the service scenario of Ricardo, for instance. I know I'm getting something out of it, so I share. If I don't get what I want out of it, I don't share. Yeah. So I think we have to simplify really the idea.
There are many motivations that precisely, it goes back to the same question that we were saying. I mean, we need to research more on what motivates people to share, businesses to share, and it's not only self-profits. As we said, the comparison with competitors, etc., and other factors, long-term factors, and all these are important, and we need to do that. I have still one question. And I'm closing the Q&A. I don't want to be unpolite, so I'll put forward this question, but I'm closing this. I will not answer more questions. The question from our nice anonymous attendee is: data will definitely increase the process generally, not all the time. How to count the inaccuracy cases in terms of the economics? Can you understand this, Pierre?
Yeah, so I think it was precision. You meant increased precision. Yeah. So I was mentioning it in my talk. We have to embed these tools for machine learning in there. So, for instance, cross validation or something like that. Because in my mechanism, like the one of Ricardo, we can naturally see if some features are making us worse off. We're going to take them out, right? So somehow that means that we tell people we won't pay you, but we don't want your data. If you were pushing it, you could actually say, you're making my accuracy worse, so now you have to pay me to make me worse off. But we don't want to do that. So like we do in machine learning, we have a cutoff. We can use lasso for that. And somehow, if you don't provide me this value, I don't want you, but then you don't get any payment, right? We agree, Ricardo. That's the way to handle it.
Well, yes. Very well. It's about time that we close our webinar. We have been having this this idea that webinars should be short. Otherwise, it will be sleepinars, not webinars. So I really appreciate the effort of the panelists, and also the patience of the attendees. It was a very important audience from many countries, from the United States to India to Brazil to whatever, you name it. So there was a very, very large audience. I thank the audience for the interest and give an incentive to come back to us and meet us again in the next webinar to be announced. This is a very interesting initiative, I believe, trying to put out results from recent research. And then, as you can see and you have witnessed today, not only some results from research at INESC TEC, but also very interesting results from our partners and friends in the world. And Pierre Panson, merci beaucoup. Thank you very much, TAC, for being with us today.
Yeah,
yeah, very nice answer. And so have a safe new year, everybody. Take care and be clever. Being safe is a matter of intelligence, not a matter of being stubborn or being afraid. It's a matter of intelligence. We are scientists and researchers, so please be intelligent. Goodbye. See you soon.
Bye.
Bye-bye.